Hello friends, as we discussed in the previous videos that for designing an optimal matching order engine, we use the first approach as using a one-dimensional linked list. But here, we've for all the implementation that we have done for matching order, cancellations, and amendments, we found that although it's like always correct, but the performance is not optimal. Because every time we want to add any order, whether after the amendment or whatever, so we have to add it to the linked list first, and at the last, and then we have to sort it. Now this sorting always takes n log n time complexity. So for example, here we have compared all these performances that whenever you want to add, it's always n log n. And similarly, when we amend on quantity, price, or quantity and price, whatever, every time for the remaining quantity which is not matched, when we want to add it to the linked list for both buy or sell orders, in that case, when we do the sorting, it always takes n log n. So for the second approach, we want to improve this time complexity, and we will be going to use PriorityQueue, and then we will see that how it improves the performance. Let's see, first of all, what is a PriorityQueue? A PriorityQueue is basically a data structure based on a Min-Heap or a Max-Heap. By default, when we talk about the PriorityQueue class in our Java API, that corresponds to Min-Heap. So what is a Min-Heap? The Min-Heap has got a property that the parent key is less than or equal to the child key. So if we talk about this Min-Heap, so this is the parent, right? And this is having two childs, 3 and 6. As we can see that this parent key is less than 3 as well as 6. So this is the property which defines the Min-Heap property. Similarly, if you look at all the other childs for example, 6 right now is a parent of 15 and 18, and 6 is both less than both of his children. So this is the Min-Heap property, only the relationship between the parent node and its child nodes. Similarly, for the Max-Heap, it's opposite, that parent key is greater than or equal to the child key. So here, again, if you take the same example, for the Max-Heap, 15 is the parent of 10 and 12, is higher than 10 and 12, is greater than 10 or 12. So that this is the property which defines a Max-Heap. So in Java, as I defined that there is already a PriorityQueue class which already supports this Min-Heap concept, which means that the orders are actually based on a priority heap according to their natural ordering. Natural ordering means that if it's a number, then it will be in ascending order, which means that the head would be always the minimum Min-Heap, the minimum number in our queue. And similarly for the Max-Heap, if we change the order by using the comparator, supply comparator, then we can reverse the order as well, which means that the elements can be stored in a descending order, which means the head of this priority queue or the 0th element of this priority queue would be the maximum element in the heap. Now, how this priority queue can help us, right? This is what we want, like why we want to use priority queue. As we have seen that in the linked list, when we try to add the order and then sort it, then it is taking n log n. But if we use priority queue, in that case, we can reduce this time complexity from n log n to just log n. So for example, we can use Min-Heap for sell order book and Max-Heap for buy order book. As we have defined our order books, so this upper part is our sell order book where we store all the sell orders. So if we design this sell order instead of linked list, if we design it as a Min-Heap, which means that the price with the lowest price, which is having the highest priority, that would be always at the head or the 0th element of this priority queue. In that case, this will work well for our purpose, because we want this sell order to be in the ascending order with the 0th element always having the highest priority. So the Min-Heap, in which the root is always, or the root of the whole priority queue is the minimum number of this whole list, that is having the highest priority. So this will definitely serve our purpose for our sell order book. Similarly for buy, we can see that the order with the highest buy order price would be having the highest priority. So in that case, we can use it as a Max-Heap. Now using this Min-Heap for sell orders and Max-Heap for buy orders, we can reduce our time complexity from n log n, which was in linked list, to log n only for the priority queues. So as mentioned, that we can use Min-Heap for sell order book and Max-Heap for buy order book. Now these are all the PriorityQueue methods. Whenever we want to enqueue or dequeue methods, enqueuing is that when we are adding an element to our priority queue, and dequeuing methods are when we want to remove any element from our priority queue. So every time when we add or remove, then it has to maintain that Max-Heap or Min-Heap property, right? That the parent should be always be less than to the 2th child for a Min-Heap, and similarly vice versa for Max-Heap. It should be greater than for the root. The parent should be always greater than the children. So to maintain that property, whenever you want to add or remove any element, it has to maintain that property, and that's why it is going to take O log n of time complexity. If you want to like go more into deep into like how does the heap priority works, how does it maintain its priority, you can go into more details. But just remember that whenever you want to enqueue or dequeue methods, for example, if you want to use offer, poll, remove, and add, because this is every time we are going to add or mutate our priority queue, in that case, it will be always O log n of time complexity. Similarly, if you want to remove or contains, in that case, it will be having O(n) time complexity. And if you just want to like peak element or size, I mean, if you want to get the size of the element, or just want to the peak, what is the minimum heap, what is the root, or what is the max heap for the maximum element, in that case, it's always only O(n) of time complexity. So using these properties, right, we can definitely improve our matching order algorithm. So as mentioned, once we use priority queue, and use these methods, right? So we are going to like reduce the adding and sorting of the orders from O(n) log n to O log n. Now let's compare just theoretically that what is the performance gain that we are going to get for all the other operations in our order book. So for linked list, if you want to add it, right? So whenever you want to add it to a linked list, we saw that we are adding it to the end of the linked list, and then we are sorting it. Sorting takes n log n time complexity. But for priority queue, as we have discussed, that it is only going to take O log n when you want to add an element to our priority queue. The only difference or the performance difference would be in this matching of the order, because as we saw that for the linked list, when you want to match any order, we always take the head of the element, and it's only like O(n) of time complexity. And if you do it multiple times, I mean, if you keep on filling the orders, it will always only going to take O(n) of time complexity for a linked list. But for priority queue, because every time you want to remove an order, so to match it, and after that, so removal, it will take like O log n of time, because it has to maintain that heap priority. So this is the only performance degrade I can say that for matching. Linked list is slightly better than priority queue. But for all the other operations, cancel is exactly same, because for cancel it has to like remove the object by going through all the whole priority queue and then remove it. So O(n) is same. But for amendment, whether it's for quantity, price, or quantity and price, it reduces from O(n) log n for linked list to O(n)(2) for priority queue. So these are all those like performance improvements that for add and all the amendments, it has reduced from huge, like from n log n, it's only O log n, and for amendments of quantity, it reduces from n log n to O(n). So definitely, except the matching case, right? This matching part, except for this part, all the other operations for add and or amendment is better for a priority queue. So now we have I just covered by theory that what are the benefits of using priority queue over linked list for some of the operations. In the next video, we'll go through the details in the code itself, that when I will implement the same logic for building our order book using priority queue. So see you all in the next video when I implement all these matching algorithms and addition and cancellations and amendments.